The first step to developing calculus on Heisenberg group would be to understand basically the linear maps on them. These are maps that respect dilation, they are homogeneous, and group action, they are group homomorphisms. We prove that they have this very particular form on Heisenberg group H1. We started the proof basically in previous lecture by proving that if L is homogeneous homomorphism, then the images of the vectors 1, 0, 0 and 0, 1, 0, the two horizontal vectors at the origin, must map to vectors that have 0 third component. So let this bracket L denote the matrix with A, B, 0, C, D, 0 in the first two columns, and then 0, 0, AD minus BC in the third. We see that LV is equal to this matrix L dot V for V, one of these unit vectors. This is actually how we constructed the matrix. So we asked what would be a matrix with the same images as L. To prove that this holds for all V, it is enough to show that the map taking V to matrix L dot V is also homogeneous and homomorphism. In fact, if we know that two homogeneous homomorphisms agree only on these two vectors, we get that they are equal everywhere because they generate everything. First of all, the third, as we've seen, can easily be computed out of these two. And then we use dilation and multiplication of all these vectors and their inverses to produce any vector in R3. So any such thing can be written as multiplication of these together with proper dilations. Let's first show homogeneity because that's very easy. Basically, the dilation map is given by matrix multiplication by R squared with zeros everywhere else. So this diagonal matrix multiplied into V is simply just delta R of V. If we consider this block decomposition, we get this commute just because in the blocks we're multiplying diagonal matrices. From this it follows that applying L to dilation of a vector is the same as applying L first to the vector and then dilating. And that checks homogeneity. Let me remind you how we multiply in Heisenberg group. You add in the first two components. In the third one, you add the twist 2 times. The way I memorize this is you go with the second vector's x. So the first component of the second vector comes first. So that's x2 multiplies into y1 and then minus this time x1 times y2. Let's call this vector p and this vector q. So the action of L on p dot q will be this matrix A, B, 0, C, D, 0, AD minus BC. Let's call this delta and 0, 0. Multiplying into this vector, so x1 plus x2, y1 plus y2, t1 plus t2 plus 2 times x2 y1 minus x1 y2. Now we need to multiply L acting on P and then group multiply it with L acting on Q. Now I want to confirm they are always equal, and that will be the end of homomorphism. Here there are no x1, x2s, and let's see here, there is some x1, x2, but then there is another one here, and the coefficients are exactly opposite, so AB minus AB, so that will go away. There will be no x1, x2. Now let's, for instance, calculate x2 times y1. So here I will get A times D. So let me record it somewhere. So x2 times y1 will get this coefficient, AD, from here. x2 times y1 will get a minus BC from here. So minus BC. But guess what? This is again delta. So you will get delta times x2 y1, and then here it is delta times x2 y1 here, showing that these quantities are always equal, and that shows it's a homomorphism. End of the proof. Very important consequences of that. It, for example, shows that a map as simple as x, y, t mapping to negative x, y, and t is not a homogeneous homomorphism. Although from R3 to R3 point of view, this is just another linear map, from Heisenberg point of view, this is not at all close to being nice. It's not even Lipschitz, we will probably show later. Another really curious consequence of this is that the determinant of this matrix is always non-negative. And this has been used in a very interesting paper to show that Lipschitz maps from H1 to H1 are sense preserving. And then that is used in turn to show that some Lipschitz maps defined on a part of H1 may never be extendable in a Lipschitz way to all of H1. That's a 2016 paper by Balog and collaborators. And thanks for watching this so far.